How's it going, everyone? This week we're going to be working on problem of so it's the werewolves problem, and specifically we're going to be doing part B, which is finding a linear time algorithm. Now I'm just going to kind of skip over the definition of the problem because I'm going to assume either you've already read it or you watched the part A video. So let's just jump right in. First of all, we know that from part A, the recurrence relation we ended up getting was T of n equals 2T of n over 2 plus O of n. And we essentially got that by using divide and conquer. We would divide the group into two equally sized subgroups and recurse on each of those subgroups while also doing n queries in each function call. And that ended up with this recurrence relation, which gave us O of n log n. So in this case, we need to get O of n, which is considerably faster. So how do we actually end up getting like this faster O of n time? Well, we don't really know what method we might be taking yet, but if we look at Master's theorem or the Master theorem, we can kind of deduce what sort of recurrence relation we might need. First of all, we know that we're going to be relying on the fact that the number of citizens is always greater than the number of werewolves. And knowing that, that kind of indicates that we're going to need to consider the group as a whole. If we want to like try to find one citizen from the group, but we only query them against some small subset within the entire group of friends, we don't necessarily know if this condition holds for that subset. We only know that it holds for the whole group. So that kind of gives us like a rough hand wavy indication that we're probably going to need to do like at least n over 2 queries if we say that we have n friends, since n over 2 queries is the minimum amount we can do in order to query everybody in the group at least once. So what does that mean? It means we're probably going to need to have some sort of O of n term in our recurrence relation. And if we have an O of n term in our actual recurrence relation, but we also want the overall time complexity to be O of n, it means that when we add our actual recursion part, we need O of n to dominate over the recursion part. And I'll leave kind of like the nitty-gritty math to you, but essentially by understanding Master's theorem, we know that this only happens when A is like significantly less than B, or pretty much when we divide n by something greater than the branching factor, where A turns out to be the branching factor. So how are we going to end up doing that? Well, we can't just kind of divide the whole group into subgroups and then immediately recurse on all of them like we did in part A. What we're going to have to do is actually find a way of eliminating people before we recurse. We're going to need to kind of like go through everybody in the group and find a way to just kind of eliminate people, not consider them at all, and then we can, make our recursion call. And if we do it that way, then we'll be able to get some sort of situation where like the O of n dominates. Now, this might have been kind of weird or hand wavy just looking at it in this form, but if we kind of just use it as a general idea for where we might want to go, then at the end, once we actually prove the recurrence relation, it will hopefully make a lot more sense. So we talked about how we're probably going to need to query everybody at least once, and the minimum way to do that would be if we have our group as just our set of friends like f1, f2, all the way to f sub, let's say f sub k. The minimum number of queries we could do where we get like some information about each friend would be just pairing them up and querying each pair against each other. So that would be like, or one way to do that easily would just be like f1 against f2, f3 against f4, so on and so forth until f sub k minus 1 against f sub k. So one assumption we made here was that k, or like the size of the group, is even. Obviously, this isn't necessarily true, but it turns out that like the odd case is pretty easy to deal with later, so we'll just kind of put that on the back burner for now and come back to it. And what we have here is, again, k over 2 queries. So we need some way to just like look at the results of these queries and eliminate people based on them. It's a little unclear how we might be able to do that now. So let's just kind of consider one of the queries. Let's say we have F1 queried against F2. So what are the possibilities for what could happen? Well, they could agree with each other, as in they could both say that like the other person is the same thing. We'll call this the agreement case. And that happens when we get F1 calling F2 a citizen and F2 calling F1 a citizen, or vice versa with werewolves. And what do we actually know about like F1 and F2 when they agree like this? Well, we know that they have to be the same thing. Or, I'll write it like this: F1 equals F2. That's a little easier. Why is that? Well, obviously, if they're both citizens, then they have to say that the other person is a citizen, which gives us this case here. But if they're both werewolves, then either or rather, if they say werewolf, then obviously they're both werewolves. Whereas if they say citizen, then either they're both werewolves and they're both lying, or they're both citizens and they're both telling the truth. That's probably a better way to put it. So we have that one case. The other parallel case is disagreement. And that occurs when one calls the other a citizen and the other calls the first one a werewolf, or vice versa. And what do we know about this case? Pretty much all we know is that F1, F2 are not both citizens. Why is that? Because if they were both citizens, then obviously they would both have to call the other person a citizen. So we have these two cases, and what can we do to eliminate people here? Well, we know that in eliminating people, we're always going to need to maintain that the number of citizens outnumbers the number of werewolves. So let's consider the disagreement case first. If we have some pair F1, F2, and they disagree, then we know that we have one werewolf and one citizen exactly in the pair. So then that means we can just eliminate the pair altogether. And we've removed one citizen and one werewolf, which means that if we started out with more citizens than werewolves, then we still have more citizens than werewolves, obviously, because C minus one, or we'll just say if C is the number of citizens and W is the number of werewolves, then C is greater than W implies C minus one is greater than W minus one. Pretty trivial. Likewise, or actually, this case is a little more difficult to see right away, but if they agree, then the way we can eliminate them is by just removing a random person from each pair. Or it doesn't need to be random. We could choose to remove like the first one all the time or the second one all the time, whatever. The main point here is that if a pair agrees, if F1 and F2 like agree with each other about being either both werewolves or both citizens, then what that means is that we can just remove one of them. And now if we do that for all of these agreement pairs, then we essentially just have the number of remaining werewolves and have the number of remaining citizens after removing the disagreement pairs. So let's kind of just visualize that out a little more. Let's say that we start out with K equals C citizens plus W werewolves. So obviously first we'll eliminate all the disagreement pairs. Let's say D is the size of these disagreement pair sets, or disagreement pair set. So that means that K prime, which we'll say is like the new K, and C prime and W prime are like the new number of citizens and the new number of werewolves. If we're analyzing this, then we know K prime is going to be equal to K, the original number of people, minus 2 times D, because for each disagreement pair, we remove both of them. And C prime is going to be at worst C minus D, because each of these pairs has at most one citizen in it, each of these disagreement pairs, whereas W prime is at best C minus D, because each of these disagreement pairs has at least one werewolf. It's either one werewolf, one citizen, or 2 werewolves. So obviously, same as before, C prime is going to be greater than W prime because C was greater than W, and we've reduced some of the K primes, or of the K number of just people in total. Now, when we deal with the agreement pairs, we have k minus 2d remaining people. So that leaves us with k prime is going to be now k minus 2d divided by 2, since, again, we just have all the remaining pairs. And like similarly, if we want to analyze c prime and w prime separately, we get c prime is at worst c minus d divided by 2, and w prime is at worst, or sorry, at best c minus d divided by 2. Again, keeping the same inequality. So now that we kind of have our general idea, we can go forward with the full inductive proof. We use a base case, which is just the exact same base case as we did from part A, I believe, where k equals 1. So trivially, we have one citizen, so we just return the one citizen. And that, again, is because C has to be greater than W. Let me write that a little better. Similarly, the inductive hypothesis, also pretty similar to part A, is just that for, let's say n is less than or equal to k, since we're doing strong induction here, algorithm returns a citizen, again, assuming C is greater than W. Now, finally, for the inductive step, we can kind of reiterate what we did before, but we have to remember there is the possible case where k is actually odd, and we have an odd number of friends. So let's just kind of consider that first. It's a pretty simple case. If k is odd, or now we can just say, I'll actually change the inductive hypothesis to just be for n is less than k, and now consider k, just to be completely correct. So if k is odd, all we have to do is just choose one random friend and query him or her against all the other friends. And similar to part A, if most people agree that that person is a citizen, then we have our citizen and we can just return them. Since we know that the number of citizens outweighs werewolves and citizens have to correctly identify other citizens. But otherwise, this person has to be a werewolf, so we can just discard them and move on. And obviously, discarding one werewolf, if we start off with more citizens than werewolves, just gives us even more citizens than werewolves. So we still have the same inequality. So if k is odd, query random fi against the group G. If fi equals a citizen, return fi, otherwise discard. Now we can move on to the case we were talking about before, where we just assume k is even. I'll say now k is even. So we pair up G into k over 2 pairs, query each pair. And if disagreement, then we have at worst one citizen, one werewolf, at best just two werewolves. So we can just discard the pair. And then if agreement, which is just the only other possible case, then discard one friend. And this just kind of goes like for each pair, we kind of follow this little pattern of like, if it's a disagreement, discard the whole thing. If it's an agreement, we just pick one person at random from the pair and discard them. And then that leaves us now with k prime, which is equal to k minus 2d over 2 friends left. Still with citizens outnumbering werewolves, as we discussed above. And since k, in the worst case, we just have d equals 0, which leaves us with k prime equals k over 2. So what that implies is that k prime is always less than or equal to k over 2, which means that by our inductive hypothesis, because obviously this is less than k. So by inductive hypothesis, our algorithm finds a citizen in the recursive case. So now that we kind of have like a rough proof by induction that you guys can hopefully understand and build off of, we can analyze the final runtime. So if we kind of go through each step meticulously, we know that our runtime t of k, in the worst case, so we'll do less than or equal to, in the worst case, k is odd, so we first have to loop through all k citizens, or choose a random citizen and loop through all k citizens to query that random citizen against. So that takes O of k time. Then after that, we would need to split up all the citizens into pairs, specifically k over 2 pairs, which is another O of k. And then we need to query each of those pairs, which is O of k over 2, same as O of k. And finally, after doing all that, we're left with our final less than or equal to k over 2 pairs remaining, which gives us t of k over 2. So that leaves us with a recurrence relation of t of k is less than or equal to t of k over 2 plus O of k. And by the master's theorem, that just equals O of k as desired. So hopefully this was a helpful walkthrough to kind of see how you might be able to approach a problem like this. It's pretty cool how we could take what we did from part A, our divide and conquer O of n log n case, and find out like clever ways to eliminate citizens, or not citizens, sorry, friends, in order to get a much more efficient case of linear time. So hopefully you enjoyed, and I'll see you next week.